Hello, my name is Seong Kim from the Advanced Water Resources Engineering Lab in Korea University. In this video,
선생님,
예?
그리고 PPT 코리안 버전인데 상관없나요?
예, 상관없습니다.
아, 네, 죄송합니다.
감사합니다.
예, 예. 그냥
네,
하십시오.
그냥 이어서 하시면 돼요.
예, 예. 오케이. 1분 맞춰서 해야지.
아, 오케이.
아니 생각보다 1초가 길어요.
맞아, 맞아.
이거 하면
어.
아휴.
이렇게 움직이면 되잖아요.
Okay. Hello, my name is Seong Kim from the Advanced Water Resources Engineering Lab in Korea University. In this video, I'm going to tell you about one of the most coolest deep learning technologies, the generative adversarial networks, which can generate realistic images by making compete for two other neural networks. The generative adversarial networks, also known as GAN, is one of the neural network frameworks for generating multidimensional data like pictures or images. Its name could be unfamiliar with you, but I'm sure that you have seen the synthesized images that at least once made by these kinds of deep learning models. For a long time, the creative generation has been considered the exclusive property of mankind, not of the machines. However, the GAN showed that computers not only can learn the features of the visual data, but also can draw it. The woman in the left figure is not a real person. Her appearance is just a result of the GAN, which learned about a lot of other models' faces. And if you modify some structures of the GAN, you can cartoonize your faces, or even you can change your favorite artwork into other painters' styles. This is what the GAN models do. And you should have to know that the background information to understand why GAN is invented. So let me introduce you to the deep learning development level or circumstances at the time. Until 2014, one of the most striking achievements in deep learning technology was the discriminative model. They can process high-dimensional and rich sensory visual data so that they can classify the specific features in the images or the videos. Simply speaking, a discriminative model is an optic nerve of the machine, just like you see something and know what it is. For example, if I show you a picture and ask you, who are these guys? And then you can answer that, yeah, it's a BTS, and that's what the discriminative models do. However, the generative models had a lesser impact than the discriminative models because there were some difficulties in probabilistic computation for making details or the uniqueness of the images. Finally, the GAN was invented as a sensational image generator using those two models both. Then I'm going to tell you the basic theories first in the next slide. Okay, at the first in the image generation technology, there was a simple concept. The neural networks are usually used to reduce, distill, and summarize the information of the input data because they had to learn the characteristics of the data with those extracted features. So the fundamental concept of the generation model is reversing its structure. Backquery is the reversed model based on the one-hot encoding vectors, which can represent the label of the image. One-hot encoding vector is a vector consisting of a single 1 and the rest of the 0. Which means that if the image number 4 is applied to the forward query network, its label was saved as number 4 by making the fourth component of the one-hot encoding vector as 1. But this kind of generator makes the ambiguous data and they are all identical. Because the neural network cannot generate realistic and unique data with this kind of simple data and expansion. So the GAN developers thought of special idea. By the way, do you know about this movie? Uh, as you can see, its title is Catch Me If You Can, and this is a very famous crime film based on the true story of the legendary fraud criminal. His name was Frank Abagnale Jr., and he disguised himself in numerous jobs such as pilot, journalist, and even doctor and lawyer. But his worst crime was occurrence forgery, making fake checks on his own. Then, what the police did? He tried to catch him. And this is the main idea of the GAN model. When the generative model makes fake data, the discriminative model tries to detect it and catch the fraud. In this kind of adversarial competition, their ability to cheat or catch each other might be greater as time goes by. The generator cheats the discriminator, and the discriminator catches the generator. So, we should construct the adversarial training process in the neural network framework. Then think about the discriminator first. If there is a cat and the image that whatever is not a cat, the discriminator can easily classify whether it is a cat or not a cat. And if there is a drawing of the cat, like this, it can be quite confusing, but the discriminator somehow succeeds. But what if the painter's ability gets higher? The discriminator will be confused more and more. In this case, the painter is the generator. GAN model is advanced by the loss function. Then the loss function will reward the generator when it wins. But otherwise, if the discriminator wins, then punish the generator. This is the simplified total process of the GAN. So the three steps for this adversarial training are like this. It's not difficult rules. And simply speaking, these steps are to inform G and D of their respective goals. But if the balance between the ability of G and D, the model cannot be advanced even the iteration is progressed. In other words, if one is too stronger than the other, the weaker one has no chance to be improved. So the balance is very important to make a successful image generation, and their levels should be similar in the whole learning process. So this is the entire model structure and training procedure. And after all, GAN works as a generator, so it would be nice to understand if you focus on the generator training process. There is the dataset consisting of the real images that the generative model wants to mimic. And the generative model, G, also makes the image using random noise. So at first, the fake samples that the generator made are more like the random pattern not depicting a specific image. Then the discriminative model D analyzes the sample and makes a decision whether it is the real image or the fake. Next, if the D detects correctly, both G and D will be affected by the backpropagation, which means the model G and D are both improved. But in the case of the G winning scenario, only D will be trained and improved. Finally, when the training is finished, model D will make the decision for all of the samples with the probability of 50-50. In other words, D becomes to say, it seems to be real, but it also looks like a fake, but I don't know, whatever, I'm just a talking potato. Okay, it means that the G makes synthetic but the realistic fake images, totally tricking D. So now the generator is ready to make a fraud. The generator in the GAN cannot see the datasets directly, but it just estimates the distribution according to the discriminator's decision. So it is like Who Am I games. G says, hey D, is is this image real or fake? And G asks D over and over again until it becomes aware of the data distribution on its own. So then it can make more creative results because they train how to generate the data more indirectly. However, most of the other generative models usually just train the distribution of the image datasets. In consequence, they are not easy to get out of the original distribution, just making variations. This is the mathematical procedure of the GAN. The main idea is called a two-player minimix game, and this is one of the rules of the theory of games by the famous John von Neumann. The models G and D are adversarial relationships, so they have to maximize their own benefits while minimizing their counterparts' benefit. This is the minimix game. So what is the benefit? The value function here indicates the resources they want to have, and the purpose of this model is to maximize the performance of the generator. So this minimix game equation will be the kind of an objective function. As this function value gets higher while the training is on, the distribution of the generated data will be closer to that of the real datasets. Then the detection criterion of the discriminator will be useless. And finally, the distribution of the D will be identical to the original data's distribution. Okay, so these are some properties of the GAN training procedure. And firstly, completely optimizing D in the inner loop is prohibited because of the overfitting. And the G is optimized once when the D is optimized for k times. It makes D maintains near to its optimal solution while G changes slowly enough. Then the optimal D function can be represented as below here, P data over P data plus PG. And if the entire model reaches the global optimality, the function value of the minimax game will be log 4. Because the probability that the model D decides that the sample is fake is the same as vice versa. In other words, if G and D reach the optimality, PG will be updated, converging to the P data. Ian Goodfellow and his colleagues tested this model with several datasets. MNIST is one of the most famous datasets in the deep learning field, which is consisted of small grayscale images of handwritten single-digit numbers. It also has been utilized to train the convolutional neural network, which is the classifying model. And TFD is also the grayscale image dataset, but there are pictures of real people's faces. And Cipher 10 consists of images that have simple classes. For example, there are some images of bicycles, dogs, cats, and trees, and so on. Then the GAN was tested with several generative models. The performance indicator was the Parson window-based log likelihood, and it is positively proportional to the model performance. The results showed that the performance of the GAN in the MNIST dataset was much better than any other candidates, while it had a good large variance. In the case of the application to the TFD dataset, the stacked CAE model showed the best performance, but the GAN also did not fall behind. And in this case, the performance variance was the lowest, representing the good stability of the GAN. In the picture below, the image and the yellow boxes are the real images, and the images on the left-hand side are the generated ones. It is not easy to distinguish even if you take a look closely. So these are the pros and cons of the proposed GAN model. The GAN does not have to use the Markov chain to improve the model in the training process, so it can mimic the distribution even if it is sharp. And they only use the backpropagation to calculate the gradient, and they can they get statistical benefits by using that. And there is no need for estimation in the learning procedure. So the various other functions can be integrated into this model. But however, there is no explicit representation of the PG, and the G and D must be synchronized well. Otherwise, the model can be easily collapsed due to the overfitting, especially the generator. By the way, the pictures on the right hand side represent the examples of where the GAN is being used nowadays. They can change the hair or makeup styles, even the animal species and the architectural style of the buildings. Also, they can make people look young or old while considering the gradient. So now, this is the algorithm structure of the GAN model. The order of the model D and G construction can be changed, but you should have to know that the D has its own loss function and training. It means that the D should be primarily trained before the adversarial training process, because it should have a fundamental classifying ability from the beginning of the training. And the G is trained by the gradient, which is the result of the D's training in the adversarial process. Then the results should be good, right? No. Something is generated and they have some patterns, but we cannot recognize what it is, and even it is not clear. Considering that the G has never seen the original dataset, it's quite good results, but it is not enough. The ideal results should not be ambiguous and identical like this. It is because of the failure in the training process, which is called the mode collapse. The mode collapse occurs because of the imbalance between the two models, although I don't know which is the problem. It can be overcome with several modifications, and we can change the loss, the activation, and the optimizer functions into the latest techniques, which can perform the higher order and more nonlinear calculations. And the normalization is also important, so we add it to the layer. Increasing the number of seeds and epochs is good, and in this case, the seeds are the starting value of each data. So it is hard to generate all the pixels of 10 digits with a little number of the seeds. And lastly, we can modify the random generation process of the seeds, and this is very important. In the discriminator, the data value of each pixel is randomly discovered without any trend, so its distribution should be uniform between 0 and 1. But in the generator, the value selected in the normal distribution with an average of 0 and the standard deviation of 1 is effective to be trained. And these are the modified results. After we change some operating functions and the number of the seeds, there is little change, but the clarity is still poor and the images are still identical. However, when the random generation process is modified, the uniqueness and the clearness are quite improved. And finally, if we increase the number of the epochs, we finally more clearly what the digits are. And these are the summary and the conclusions. The generative adversarial network, also known as GAN, is a deep learning model framework based on the adversarial process for multi-dimensional data generation, like the images. The generative model G is trained to maximize the mistakes of the discriminative model D until the D cannot detect the fake data generated by the G. And GAN model mimics the distribution of the training data more successfully than other latest generative models, synthesizing realistic and unique results. And utilizing the GAN's data generation mechanisms can assist various studies in other engineering fields, including water resources engineering, such as providing additional synthetic data for semi-supervised learning or image translation from one status to another. Okay, this is the end of my video, and thank you for watching this video about the generative adversarial network for image generation. And I hope that the people who watch this video will be interested in deep learning technologies in GAN and other fields, and they will be successfully applied in their respective fields. Thank you.
끝.
아